Okay, so since I forgot to hit the record button, let me remind you what we're doing here at the beginning. We are taking these 6, we're going to draw them. We're going to get the electron pair geometry, molecular shape, and whether or not it's polar. So why don't you guys start with that, and we will move forward from that. I'll give you guys a head start, and then I'll start filling it in. All right, let's wade in here. Wade in the water. Hey, I finally finished American Idol. Did anybody else watch it?
No.
No, okay. What should I watch next?
Are you watching the Bachelor recaps?
No, the wife is though. I have a hard enough keeping up with it in the first place.
Do 90 Day Fiance.
Say that again?
You should watch 90 Day Fiance.
What is that?
It's crazy.
I only get Hulu and Netflix, so.
Ah.
Yeah, I only get Hulu and Netflix, and I only get a chance to watch TV for about a half an hour a day. So give me a show that I can watch for half an hour a day. I'll do it. Guess that pretty much narrows it down to Futurama and Archer.
Parks and Rec.
Oh yeah, Parks and Rec. Oh man, I turn on this fan, no wonder. It's already hot in this room. Let's get the other ones. Hopefully no one's getting too confused. Hopefully you guys are already ahead of me. Dead air day. Once again all day. Nobody talking, everybody writing. Dead air day. Hey, we're up to 20. Someone just popped in. Who just popped in? Might have been Neil. No, Neil's been here.
Sorry, that was me. My internet got kicked me off and then I had to get back on again.
Oh, that's fine. Just glad to have you.
Mm-hmm.
So that means we're finally all here because I know we're going to miss Graham today, and that makes our 21. So I'm down to my core group.
How was your Father's Day? Did you get another song?
No, we're beyond songs. I didn't get a song. I didn't get a brew day. Basically, everyone woke up and went, oh, it's just a day. I was like,
Oh.
thanks, guys. I know they didn't mean it.
Yeah.
Let's face it, Father's Day is a made-up thing anyway.
Mm-hmm.
They made it up just like they made up Mother's Day so they can sell stuff. Did anybody do something nice for their dad on Father's Day?
Yeah.
The deafening silence says, no, dads? What?
We threw my dad a party and got him gifts.
Nice. That is one lucky man. How many kids?
It's me and two brothers, so 3.
Are you the oldest or youngest?
Oldest.
Setting the tone. The burden weighs heavily upon us older people, older brothers and sisters.
Yeah, especially because I'm older by 6 and 8 years.
Oh, wow. I guess technically you're the accident.
Yeah.
I'm just kidding. We're all probably accidents if you think about in many ways how hard it is to A, become pregnant, and then B, get through it all, and C, live past the first year. There's a reason why the first year is a big birthday. Statistically, if you make it past year 1, you'll live. But until then, it's like all bets are off. It's really weird. All these sobering, depressing details you learn when you become a parent.
Yeah.
So I got 4 more months to go. Then my kid's gonna be out of the clear. All right, so as we look at these, I know you're in a little bit late for this, but if we take a look, do we have any burning questions as to what, who, where, or why?
Yes.
Thank you, Frank. Now I know all's right in the world.
Everything after what is like molecular or the whole planar thing. I'm sorry, not planar. Everything after the polar thing. Like I don't get the polar thing.
The polar thing is if the bond is a polar bond. So if you have those electronegativities that are vastly different. Now I haven't put any of them up here because I've used for this for all these examples, obvious ones. We know fluorine's a greedy bastard. We know carbon is kind of So we know already that these two right here on this side are going to be pulling and be slightly negative on this side. Whether or not sulfur is pulling hard against carbon, which it really kind of isn't, It's barely on the polar region if you really want to stress it. It doesn't matter. It's still not as strong as fluorine. So since it's unbalanced, this will make it polar.
And carbon is neutral because, or I'm sorry, and hydrogen is neutral because it'll never have any additional electrons.
It's not that it's neutral. It's just it doesn't pull so hard. So I wonder if I can actually find one real quick. Hold on. Let's see.
There was a compound that had hydrogen in it as an example, and it said non there. I'm trying to pull it up.
I'm gonna look and see if there's actually an electronegativity table. Hey, there we go. Look at that. That was pretty easy. Dang. There we go. Give it to me. No, quit making me click so many times. So here is that table I was referring to where I said fluorine was a 4.0 and cesium got down to a 0.7. Anywhere in between here, when they basically do the measurements that they do, they assign them in between those two scales. So it's not that hydrogen is neutral, it's just that it doesn't pull very hard. It only pulls at a 2.1 versus say the 4.0 of fluorine. Now it does turn out that sulfur and carbon happen to be just about the same on their electronegativity. So technically that side would be nonpolar, but that CF bond is very polar.
So I'm seeing compounds with like 3-4 different elements, and how do we find the difference between all those?
Well, if you need them on the exam, I will give them. If you don't, it's going to be one of the painfully obvious ones. It'll be one of the painfully obvious ones, which is, oops.
The 4 that were up there.
There, those 4.
Okay.
So it'll be these 4, or I'll have to give you the values. Because there's no way you should know, there's no way you can know all those electronegativities.
Okay.
HOF, HOF should be painted, as I said, as polar because we have lone pairs on the central atom. So no matter what, that's going to be a problem. NCl3 polar because again, we got the lone pairs. Chlorine is going to pull really hard. Nitrogen is going to try, but it's got nothing up here to balance it. Hopefully SiSe2 and nitrogen, those are clearly nonpolar because they're symmetrical, and especially nonpolar for nitrogen because it's the diatomic. And you know, you got a really greedy and a mostly greedy pulling against hydrogen in the last one, so that's why that one's polar.
So
what about the shapes? Go ahead.
So that the lone electrons on a central atom is not a 100% though, because I'm looking at the neon. I'm sorry, the nitrogen, and
Yeah.
I see, because I see 2 pairs of lone electrons.
Yeah, but they're twins pulling.
Okay.
Who's gonna win?
No one.
No one's gonna win. They're pulling exactly the same, so no one's gonna win. Uh-oh, I see something in the chat. Oh, why is SiSe2 linear, but SeS2 is not? Well, I'm only gonna tell Julio, Ellen, because I'm just kidding. I'm gonna tell you all. All right, here we go. So that was a question. First of all, Julio, why don't you just jump in there and ask that?
Because he had to go to the bathroom, so I'm taking notes for him.
Oh, hey, who's that then?
Kendall Gunderson.
Wait, are you in this class too, right?
Yeah, we take notes together because my computer doesn't work sometimes.
Oh, okay. Wow. So you're not my first shelter-in-place couple, so that's cool. But that explains why you disappeared off of, because you were in lecture at one point, and then you just sort of disappeared. All right, so was it Julio or was it you, Kendall, that wanted to know that answer?
It's Julio, but he wanted me to take notes so that he could know.
Julio wants to know.
Thanks.
So did Ellen. SISE2 linear. SE2 not. Okay, so if we look at SI, the SE and the SE, okay. I just want to point out that SISE2, we got 6, 12 plus 4 is 16 electrons, and this guy has 18 electrons. Ellen, you'll have to answer for, or actually Kendall too, you'll have to answer for Julio. Are you guys okay with that 16 and 18? Does anyone not know where I got those?
I got it.
Okay. So I'm going to go ahead and draw SISE2 instinctually on left and right, just because. And then I'm going to backfill my electrons. So I'm going to have, let's see, that's 2, 4, 6, 8, 10, 12, 14, 16. Oh, we're out. We're out of electrons. What I'm going to do now, though, is I'm going to fulfill octets. I'm going to take these two guys, put them onto the bond, those two, put them onto the bond, take them away, put them on. And so we can have SE to the SI to the SE. Okay, now, in contrast, let's go ahead with that SE2. So I'm going to go ahead and sophomoreically put this here. Now, if I were clever, I'd remember that sulfur looks like oxygen, and so I would go like this and put them left and down. But let's just say that you're on the exam, you're panicking, you do the left and right because why not? It's okay. So we have 2, 4, 6, 8, 10, 12, 14, 16. We got 2 more left. We have to put them here. Now, when we put them there, you got to know that those guys take up space. So it can't be linear anymore. Those lone pairs will bend that. So those lone pairs taking up room are going to bend that molecule. And of course, this is going to have a resonance structure. I've already drawn this. So because we had that extra electrons, because sulfur, just like oxygen, wants to bend something if it's in the middle, because when we fulfilled our octets, we had it on the top, we had to move the rest of those atoms away because lone pairs take up space. All of those are answers as to why the sulfur being in the middle will bend it, but the silicon, not so much. And again, if we go back to yesterday, at the end when I gave you your reference sheet, where'd the reference sheet go? Oh, it's in VSEPR. When I gave you the reference sheet, right here, we know that carbon looks, or silicon looks like carbon. And so silicon can do any of these configurations just like carbon can do any of these configurations. Oxygen and sulfur look the same. So sulfur would do just like oxygen and take these configurations. So Julio, does that answer your question? Kendall, you're supposed to jump in with your deepest voice. And
I'm going to say yes, but I don't know.
Well, does it make sense to you?
Kind of. I'm still kind of trying to figure this out. So.
Okay. Ellen, did it answer your question?
Yes, it did.
Okay.
Thanks.
So Julio / Kendall, you can get Ellen. She'll dial you in there. She's got this.
Okay.
And I can also, like I said, this lecture should go a little shorter, so I'll be able to do some review with you guys after that.
I just,
Okay.
if anyone else is having trouble with IMFs, like as soon as IMFs were introduced, if they just like totally lost it, please speak up because that's where I was yesterday.
No, just you, Frank.
Great. Thanks, guys. No, like, gonna make me feel better. Or...
Oh gosh. Oh man, there's like 15 hands that should have gone up, so don't feel
Right?
bad.
Okay, because I was like, I even rewatched the lectures and I was just like, huh?
Oh man, I rewatched them and I'm like, what was I saying? All right. So let's go back to IMFs. Let's finish the IMFs.
Oh, I'm sorry. I do have a question. If you can go back. Can we talk about the reference sheet from yesterday real quick? Just because you're talking about it.
That was on VSEPR, right? Yeah.
Yeah. So I'm looking at the carbon, the 4 bonds that carbon has.
Yeah.
So it can take all 4 of those are correct forms. Is that what you're saying?
Yes.
Okay. That's it.
Oh,
That's my question.
man, I love those questions. All right. So I just want to recap here because I have technology and sometimes that's a good thing. Yesterday we talked about the ions and dipoles. So whenever you have an ionic compound, so that's a metal and a non-metal, if it's going to dissolve in a polar solvent, something has a dipole, what will happen, and especially in the case of water, is that the slightly negative parts will go to the positive portion of the soluble salt, and the delta positives will go to the negative part, creating what we call the solvent cage. This is the physical way that these ions will go into solution, and you'll watch that compound essentially disappear, dissolve. You have to have a bunch of them around it in order to keep it happy, because remember, we're taking it away from an actual plus and an actual minus. So we have to surround it with a lot of slightly positives and slightly negatives to keep it happy. As I told someone in office hours yesterday, it's kind of like asking a couple of people to not be around each other. And someone gives a call and says, "Hey, we're all going to go out and so you gotta leave that one behind and come out with us." You don't do that for just one friend. You have to have like a ton of your friends calling you up and nagging you to go out and say, like, leave that person behind. We're going to take you out. Eventually you go like, well, okay, fine, I'll go out, but the only rule is you can't leave me alone. So they surround you, they keep you happy, they keep you comfortable. And then at the end of the day, we'll go right back to where you were in the first place. So that's the solvent cage, that's the ion dipole. And again, they're pretty weak as far as an interaction because it's pretty easy to get it back. You just get rid of your solvent. We talked about dipole and dipole, that's 2 polar. And again, the delta positives and delta negatives will try to interact as much as possible. Keep in mind that these solutions do move a lot. So for every time you get a positive interaction, you might get a negative interaction. Don't worry, that thing's gonna flip around and try to maximize the good interactions and minimize the bad ones. We can do that with a bunch of different polar molecules. Here we had water, we threw in ammonia, we threw in alcohol with it, and every time trying to get those delta positives and delta negatives to maximize their interactions.
And even though these are constantly moving, it's still a strong connection, I guess.
Well, yeah. I mean, if you think about it, is it easy to boil water and make those water molecules leave their friends?
Yeah.
No, it's not.
Oh, right. I
put water on a stove and I put a veritable boatload of fire underneath it, and then I wait 5 minutes before I finally get steam coming off. That's not easy. That's not easy. Is it easy? Is it easy to get the salt back here? Yeah, you just leave it outside for a day and the water goes away. Duh. It's pretty easy. This is hard. This is very hard. Those bonds are very strong. We also said at the end of that if you happen to have one of the greedy bastards, N, O, and F with hydrogen, and both compounds have to have this. But if they do, those greedy ones are too busy trying to steal everyone else's hydrogen. It tangles everyone up and creates what we call the hydrogen bond, which is really just a force. But the hydrogen bond will look like a tangled network of extra forces holding these things together. Now, let's finish this up. Next, we have the dipole-induced dipole. The dipole-induced dipole. All right, Alex, you happen to be at the top of my list over there. What do you think this is involving?
I don't know. Can you actually hear me? Because my mom's teaching right now. So.
You know what? I'm going to put you in Brenna's situation, so you're off the hook.
Okay.
All right. So then I'm going to go with Ellen, because that name's still on my front list here. What do you think dipole and induced dipole is referring to?
I have no idea.
Oh. Yes, you do. Here we go. Ion dipole means an ion with a
Polar molecule.
polar. There you go. Remember, dipole. That means polar. So if we go back here, we know half of this now. Dipole-induced dipole means we have a polar with
Polar?
Non-polar.
non-polar. Now, because dipole-dipole meant polar-polar, dipole-induced dipole, we must be talking about the other one. Now, what does it mean to induce?
Make.
Make.
Like, yeah.
Where have we heard the word induced with?
Labor.
That's right. For whatever reason, it's like the only example we all seem to know. Inducing labor, meaning causing it to happen. So what dipole-induced dipole does is a polar molecule will get together with a nonpolar and force that nonpolar, induce it to being polar for a very short period of time. These, by the way, are very weak. These are very weak. And I'm going to go ahead and use water and carbon dioxide as, so let's just say that I have water and I have my carbon dioxide. Now, since we've been working with these a lot, I'm going to go ahead and put the delta pluses and minuses there. I'm not going to worry about that carbon because, as I said yesterday, we really can't see that carbon. But on either end of that CO2, it is negative. And on either side of the water, you either have a positive or a negative portion. Now, what's going to happen if that water molecule gets together with that carbon dioxide? What happens if it gets close enough to, say, interact with it? What do you think is going to happen in this scenario that I'm putting up right now? Do they want to get together? I have the negative portion, the oxygen. Looking at the negative portion of the other oxygen, do those things want to get together?
No.
No. So, what might the water molecule do instead?
Go to the hydrogens.
That's right. So, this is not good. Not favorable. What would be favorable is, say, this. Because here we have a negative and here we have a positive. So let me go ahead and get a little video going on here. So you can imagine that if the carbon dioxide and the water molecule happen to get together like this, immediately that water molecule will want to flip around to try to maximize its interactions. Okay? There's good and bad about this. While that's favorable and the other one's unfavorable, it doesn't mean the other one can't happen. Because here's what's going to occur. I'm going to stop there real quick. So this is kind of favorable. But remember, everything here is fluid. And when we talk about these electrons being hoarded around one side or hoarded around another, that implies, correctly, that they move. It implies that they are not locked into one configuration. So let me ask you this. If your electrons on that carbon dioxide, and over here on the left, you happen to bump into one of these water molecules in this unfavorable situation, what are the electrons going to do? They're going to run away from the bad influence. They're going to run away from that other negative they just saw. And specifically on the carbon dioxide, they have room to do that. There's not much room on a water molecule to do that. But on a carbon dioxide, if these electrons are sitting out here in almost like a peanutty type shape, with a whole bunch of them out here off to the left, they have the option of running in to the safety of the inside of the molecule and still keeping their octet. They have the ability to move. Now, likewise, over here, if we have these electrons floating around the CO2, what do you think these electrons do when they see this positive over here? They're like, ooh, why don't we get a little closer to that? Now, when this ever so slight movement of these electrons occurs, carbon sitting there in the middle starts to now notice a difference. Starts to now see that those electrons are not completely equally distributed on either side because I've got this tug of war between the oxygens on either side of me. No, they've started to move a little bit. They've started to crowd around one side or the other just a little bit. And when they do that, it induces a very temporary, very weak dipole. So, trying to get all that down in words. When the electrons on CO2 see either delta plus or delta minus, oh, that's bad delta, on the water, the electrons move toward or away. From said delta, causing a very temporary, very weak dipole. When it does this, that means now it has the option of getting together with that water and sort of hanging out a little bit. But as soon as those electrons do that, carbon is going to wake up and go, wait, what are you doing? What are you doing? The electron's like, oh, I'm running away from this bad negative charge. And carbon says, get back there. What are you doing? Ooh, there's a bright, shiny positive charge. Get back there. And P.S., by the time carbon even has a chance to look, remember, everything here is moving. By the time carbon has a chance to even look, this negative could have easily flipped around and been a positive, or vice versa. Everything's constantly moving. So these interactions are very temporary and very weak, but they occur, they happen. Carbon dioxide and water, we do it all the time. It's called soda, it's called beer. That's the carbonation, guys. You're pumping CO2 in there. Now, does it like to stay in there? No, but you'll always have some. We pack it under a lot of pressure to try to keep it in there for as long as possible, but as soon as we release the pressure, as many of those CO2s that can get out do get out because they are nonpolar. They don't want to be with the polar, except for those very few. They get trapped in this very temporary, very weak induced dipole. And those will constantly be swimming around being induced by the water to stay. So this is an example of when you have things that you wouldn't normally think getting together. Not so much, not very strong, not very favorable, but just some will make it. The last one we have.
Can you repeat that, what you just said? When you said when you have two things that want to be together.
So if you think about water, let's go back to it again. If you think about water, water definitely has every impetus to be together, every incentive to want to be together. They all have pluses, they all have minuses. Heck, they even have that hydrogen bond. That's great. They want to be together. Polar likes polar. I mean, even here, if we go back to the ions with the dipoles, look, you got dipoles on this water up here, and they're very much attracted to an actual charge. They really want to do that. But the question is, what happens when you get something that probably doesn't want to get together? You got a polar here with something that is nonpolar. Why would they want to get together? Well, the fact of the matter is they don't want to, at least not in the sense that you and I would consider want to, but they can induce just a few of them to stick around, to interact. And this is how you get dissolved gases in water all the time. You know, when they talk about the acidification of the oceans, and we'll talk about that in a week or two, they're actually talking about that carbon dioxide dissolving into the water. And the more carbon dioxide you have in the air, the more can be put into the water. And when you make this little combo, this is actually carbonic acid. And it's because you have all this water that can induce this dipole onto the carbon dioxide and entice them to come into the water, even though they technically don't want to because they're not a polar molecule. Who was that? Who asked that question?
That was me.
Oh man, you didn't pop up fast enough. I'm gonna assume that's Maria. No, it's Laura.
No, it was me.
Ah.
Giselle.
Wait, who? Oh, Giselle, okay.
Yes.
See, normally when you speak, your name will pop to the top of my list so I can see who you are, but you're hopping back to quiet faster than the computer can see it. So I'm like, ah. All I hear is it's me, and I'm like,
Who?
kind of like when you get that phone call from a friend and it doesn't show up on your caller. Back in my day, we didn't have caller ID, and someone would call you up and like, hey, it's me, and you're like, who? Yeah. Anyway.
Thank you.
Did that answer your question though?
Yes.
Okay. Well, then I'm going to ask you.
Okay.
If dipole induced dipolar, then what is induced dipole with induced dipole?
Two nonpolars wanting to get together for a very small time or a short time.
Actually, what's interesting about that, yeah, you're right. It is non plus non. Interesting about that is it's not that they get together for a very short time, because many of them stay together forever. And this is the weird part about it. I'm going to show you this. Okay, so if I were to draw 5 of these guys, this is a carbon chain, a hydrocarbon chain, so it's got carbons and hydrogens on it. It's called a hydrocarbon chain. We'll talk about it in the last lecture of this class. Hydrogens, I mean, I don't want to put all the hydrogens there because it's just going to muck it up. There are hydrogens here. Octets. Clearly here with just C's and H's, these are all nonpolar. With only CH, these two are nonpolar. Pentane, which is what this is a liquid. I can go back in this stockroom right now and grab it. In fact, let me just go ahead and not make it pentane. Let's go ahead and make it hexane because that's even easier. Because hexane is one of the things that you quote used when you did the flame test lab that finally got unhidden or unlocked. Don't talk to me about that. It took me 30 minutes to figure it out. But it's a liquid. So when we're asking about the interactions here, but by the way, let me point out that induced dipoles, these are stupid weak. So and then I'm going to have to address this here. These are stupid weak. Okay. Now, and that was Giselle. So I'm gonna keep on with you, Giselle. Because you up until you made this one fateful mistake, and you didn't know, so it's not really a mistake. It's just you didn't know yet. Induced dipoles, two nonpolars coming together. Now the idea here is, why would they even want to get near each other at all if they have no pluses and no minuses? What could possibly be the attractive force here? And the answer is exactly. Until you remember that if these two things come together, if we get them in close, those electrons that are just sort of swimming around this thing, right? They're all moving. What's going to happen when those electrons see one another?
They're going to repel.
That's right. They're going to run away from each other. You've got negative charges here that want to run away from each other. So, oh man, Meng's probably cringing over here because she knows everything that I want to do for this, and I can't. So I'm going to do my best here. So you can imagine these two hydrocarbon chains. Now I'm gonna keep my hands as the chains and sort of bend them a little bit here. When they come together, when they get close enough to actually see each other, the electrons are going to repel. They're going to run away to the other side of the molecule. At which point carbon's going to go, what are you doing? Go back to where you're supposed to be. And they're like, big scary electrons. It's going to go like, no, get back there. And it's going to start setting up some things to where eventually they get in sync. That after they scare each other enough, they're going to start realizing that in that weird split-second difference of one getting back there before the other, that induction of the dipole actually means that they can go positive, negative in sync. And they can just do this over and over and over to each other. And it's when they get into sync that they now have the impetus to stay together. They have a reason to be together. Okay. So now, when they get together, remember, electrons are moving. Remember, electrons move. These will induce, yeah, that's a bad view. These will induce dipoles on one another and now be attracted. And here's where you weren't wrong, Giselle. These are very weak forces, but it doesn't mean that they won't stay together forever, because they do. This hexane is a liquid. You'll see it in that lab module. I can get it right now. from the stockroom and bring it out. It's a liquid. It by no means doesn't want to stay together. It will stay together. It likes staying together. And it likes staying together because it will induce enough of a dipole on itself over and over and over to stay together. And here's where one of my things is going to maybe fall completely flat. You have to know something about intermolecular forces. Yes, we have over here water and alcohol and all those with their dipole, very strong. Hydrogen bonds, very strong. And then you come over here to these induced dipoles and you're like, well, those are weak. So what's the deal? If you think about this, there's sort of a red herring that I've put up here. When I talk about their strengths, I'm talking about the strength of a singular, essentially a singular bond within a very small molecule. So water is a very small molecule, but it's held together very well because of its hydrogen bonds. It's held together very well because it can really maximize those interactions. But most of the plastics that we have, all of those keyboard caps on your laptops, most of the components in your car, they're plastic. They're made out of all nonpolar stuff. Oil is nonpolar. And yet, which one boils first, water or oil?
Water.
Water. But Professor Forrest, you said the water was really, really strong, and that the oil with like its induced dipoles is very weak. So what do you mean? Water is really small. Oil, really big. And so you got to take this into account. When I say that they're very weak, stupid weak, or whatever, it's because I'm saying this little bond right here, if this were to try to induce a dipole on the other side, the trick with these induced dipoles is these molecules, if they're going to stay together, they have a secret. They don't run one deep. They aren't sitting over here like water with just one little bond that they can do, one little intermolecular force that they can do. It's not a bond, it's a force, one little force. They come in, they're gonna roll 6, 7, 100 deep. It's kind of like Velcro. One little hook and loop, not a problem. Try ripping the whole thing off at once. It's not gonna happen. Because even though the individual intermolecular force is not good, they roll really deep. And so that's how you can have these induced dipole interactions, and yet their intermolecular force overall is very strong because there's just a lot of them. Now, I want to point something out about intermolecular forces here. Something to note. The bigger you are, the stronger your IMFs. The bigger you are, the stronger your intermolecular forces will be. That's what I was just saying with those big nonpolar molecules inducing dipoles on one another. It's because they're so big, there's so many interactions it can make. Let's go to the periodic table. I'm going to look at hydrogen, fluorine, chlorine, bromine, iodine. Hydrogen is a gas, fluorine is a gas, chlorine is a gas, bromine is a liquid, and as you guys saw from lab, iodine is a solid. All of these are induced dipole interactions. They are all truly nonpolar molecules. But by the time you get down to bromine, and then eventually iodine, you are massive enough to now induce dipoles on your fellow bromines and iodines to now make it enough of an attractive force to become a liquid or to become a solid. The bigger you are, the greater your influence. That's the trick with a lot of these induced dipoles, is they're just big, big molecules. Now, I want to point something else out while we're here. That whole hydrogen bond thing. This is where it gets kind of fun. There's H2O, H2S, and H2SE, all the same compound. H2SE, hydrogen selenide, is a gas. H2S, hydrogen sulfide, is a gas. H2O, water, is
Liquid.
a liquid. So this is where you have the subtle power of one column over here. You have a situation where the bigger you are, the stronger your intermolecular force, and yet here, the bigger we are, the less. These two down here, H2S and H2SE, are gases. They don't want to talk to each other. Water talks to each other real good. They make a liquid. And again, that has everything to do with the fact that that can hydrogen bond. The fact that that can form those hydrogen bonds, those strong interactions, even though it's really, really tiny, even though it shouldn't have that much of an attractive force, because of those hydrogen bonds, that is such the crucial aspect of water. Because without it, this stuff would have boiled away like 150 degrees ago. We wouldn't be here. Water is bent and water is very polar, and water makes hydrogen bonds. The three things that we need it to do to keep life here. But the bigger you are, the stronger your intermolecular forces. Hence why something like hexane can be together and be a liquid. And as soon as you get up to oil, which is like 30 carbons long or so, it gets really strong. You can't even boil it.
Can you go back up to the dipole induced dipole really quick for a second?
Like that?
Yes. Thank you.
What would you, oh, you're just writing it down?
Yeah.
Okay. Now, what I want to do is take these intermolecular forces and I want to talk about how they relate to physical properties that you and I see. So let's see what they do to molecules as we know them. How do IMFs affect physical properties? All right. The first one I want to ask about is boiling point. As the intermolecular force increases, as it gets stronger, what happens to the boiling point? Will the boiling point go up or will it go down? Will it increase or will it decrease?
Did he just tell us it was going to go up?
It's going to have to increase.
But let's talk about why. I accidentally already told you the answer, but I think that was you, Miguel?
Yes.
Yes. Why is it that the boiling point will increase if the intermolecular forces get stronger?
Because since the forces are stronger, the harder it is to break up the bonds.
Yes. Well, at least break up the molecules. We're not breaking the bonds.
Or, yeah,
so
right.
I want to be careful. Yeah, that's exactly right. As the intermolecular forces get stronger, it is harder and harder to pull them away from their bodies. As the intermolecular forces get stronger, it is harder to take them away. Hopefully that's intuitive. We know what boiling point is. So let's talk about surface tension. Ooh. Let's go with, who haven't I called on in a while? Carla. What is surface tension?
How strong something is?
Okay. At the, how strong it is at the surface. So I love how sometimes we define something and we're like, oh, it's so hard. This one's actually easy. This is the tension of molecules at the surface. Now, there's a couple of ways that we have actually seen this. I just want to point out that we do know what this is, even if we didn't know what it was called. Let's see. I'm going to draw a little thing here. Well, that's a really horrible drawing. Let me try that again. There we go. Put a little antennas up there. Ooh, does anyone know what I've just drawn?
A sun?
The bugs that go on top of the water.
A cell?
Looks like
Something terrifying.
Like an ant?
It's something terrifying. No, it's the second
whirlpool.
person.
the bugs.
Looks like a potato sack.
Yeah, right. This guy right here is a water bug sitting on top of water.
Oh yeah.
I know. I'm not the best on that one.
Now that you say that, I can just picture it. We used to see them all the time, like at at the lake and the creeks and stuff.
Hey, look at this. I got the power of the internets.
Mm-hmm.
Let's see. Water strider, water skeeter. What are we going to call it here? I'm going to go with water strider. Look at that. Let's go with the images because we all know what it is now. There's bugs that can just sort of hang out on top of the water. Oh, wow. They only have 2 legs that sit out. I didn't know that. Or 4, sorry. No, it's got 6. It's got 6 over there. All right. We've all seen this.
Mm-hmm.
Okay. If you haven't, go to some swampy-like area, you'll see it. So you got the water bug sitting on top of the water. If you're even clever, you may have done this at some point in your careers. Anybody? Have you seen this?
No.
Yes.
Oh, let's do the internets. Ha ha. Because someone has decided to take a picture of it. Ta-da!
Oh, cool. I've never seen that.
Oh man, go home and do it. You can absolutely do this. You can take, well, hey. Oh, is this going to work? Because this is kind of, you would think that after a while, it would just roll off. But take a look at what's going on. And this is really cool to see. You can do this at home. You can just put drops on water and it will do this. It's kind of cool.
It's relaxing.
Huh?
It's relaxing.
Mm-hmm. I know. It's like easy to watch.
There are things like this that I could watch all day long. Look at it bulging out here on the side. Look at it out here. And yet it still hasn't fallen off.
Keep going.
Right? You guys, now everyone just wants, it's like NASCAR. You just want to watch them wreck.
Well, now I want to try it.
Man, look at that thing just bulge out, and then finally it fails.
I think he got up to like 35.
Now, as we look at that, the question is, why did the water not just run off the edge? Because water molecules like to stick to each other, right? And so even though gravity's pulling on it, the other ones are like, I got you, bro. And they're like holding them off the edge of the cliff going, no, we will stand together. And they will hold on to each other until gravity finally wins. This is the reason why, guys, when you stick your finger over the top of the straw and water doesn't come out the bottom, that's because water molecules are holding on to each other. It's one of the reasons why. They're holding on to each other. And if you've never done the penny before, maybe on some Mother's Day, you decided to bring mom some coffee in bed and you filled that cup so full because you love your mommy. And mom's like freaking out because she just sees it like bubbling on the top and you're just gently walking in like, I'm going to do this. Surface tension. It's a beautiful thing. As the intermolecular forces increase, what do you think happens to that surface tension? Is it stronger or weaker?
Stronger.
Stronger. So if they're stronger, they can hold on to each other. Stronger. The tension at that surface will be very strong. Viscosity. Woo. Oh man. What is viscosity? I love this. I love this question.
Can you scroll back up for a minute, please?
To there?
A little bit further. I think that's it.
To there?
Yeah, no, go back. Surface tension.
Okay.
Sorry, thank you.
That's fine. So, what is viscosity?
Whenever I hear viscosity, I think of like slime, like something that's viscous, right?
Yes, slime is very viscous.
So,
It's like a very thick liquid.
Okay. We typically like to think of it in terms like, oh, it's like a really thick liquid. That's actually a perfect layman's definition of it. I'm going to give you the formal definition just because it'll help a little bit here. Viscosity is the resistance to flow. Now, if you think about that, it's something like this. Remember we talked about the liquids and how unlike solids that are locked together, liquids move past each other. They have this fluidity about them where they can slide past one another. They still have to touch, but they can slide past one another. Now, viscosity is the resistance to flowing past each other. Not that they won't, but that they just don't want to do it very much. We commonly call that a very thick fluid, right? A thick fluid. So can you give me an example of a thick fluid, if you will?
Syrup.
Honey, right? Honey, syrup, those two things, they are thick. They're very viscous. Now, when we say resistance to flow, that means you dump the bottle over, how fast does it come running out? If you run your hand through it, how much does it resist you trying to flow through it? Or make them flow around you, if you will. The resistance is because as you try to move past, the other's like, no, don't leave me. And so they slow you down. They resist you moving past them. Or if you're trying to go through them, making them part to go around you. So if we go with that, as the intermolecular forces increase as they get stronger, what happens to the viscosity? Does it get more viscous or less viscous?
More.
More. The stronger they are, the more they are going to resist you. Now, here's the great part, guys. We don't have to know what they are. We don't have to know what the intermolecular forces are. We can judge them based just off of these physical properties. The last one I want to talk about is surface tension. All right, sorry, vapor pressure. Now, I'm going to spoil this one. This is the pressure of a vapor over its liquid. And I want you to think perfume. If you spill perfume on the table, you're going to smell it. Why? Those molecules are going to leave the liquid and go into the air. And they will create a pressure. We'll talk about that when we get to the ideal gas laws. Think perfume. You spill it. Some goes into the air. And that's your vapor pressure. You smell it. So, as the intermolecular forces increase, is that vapor pressure, the amount that goes into the air, does that go up or does that go down as the intermolecular forces increase?
Down.
Down. Why, Miguel? Why'd you say down, Miguel?
Sorry, I was muted. Because as they're holding on tighter together, there's less that's floating up into the air that can escape.
That's right. Less that can escape. So as the intermolecular forces are strong, if it's really strong, then the other molecules around it are going like, no, you're not going up there. You're staying down here with us. But I want to go. No. But if they're weak, it's just like a free-for-all. They all just go up there. So as the intermolecular forces go up, these guys actually go down. They're opposite. Now, let us compare. Who has stronger IMFs? Okay, I don't care what they are because I don't know all of them, because it's not always black and white as to, oh, it's just this or just that. Oftentimes there's a combination of intermolecular forces at play. What I'm going to do is I'm going to give you guys a few to compare. Who's stronger? H2O versus alcohol. And when I say let's compare, I want us to compare them with these four things that we've been talking about. Again, you don't have to know what, you just have to know that it does. Because there might be a question like this on the exam. Water versus alcohol. Who has the stronger IMFs and why? I'm gonna let Miguel start it off. And then someone else will take some of the next ones. And he's muted. Nope.
Stronger IMFs. Alcohol? No, water.
Now, why water?
Because it has a higher boiling point.
Mm-hmm. Higher boiling point? Why else?
Higher surface tension.
Okay. Are you sure about that?
Yeah.
How do you know that? I mean, you might have the life experience. They pretty much look the same even when you spill them. So I would say that surface tension and viscosity won't serve you here, but one other would.
Vapor pressure.
Yeah, you're gonna smell that
Yeah,
alcohol.
you can smell alcohol.
Right? So you have a couple there that you can use. All right, how about oil versus gasoline? Sarat. Oh, wait, no, Giselle popped in. Look at that. Go for it, Giselle.
Oh, sorry. I wanted to ask a question. So if you can smell it, then that means it has a low IMF.
Yes, if you can smell it, it has the lower IMF, because that means that their buddies down there in the liquid don't really care if they leave and go up into the atmosphere. So they're like, yeah, whatever. We weren't really that tight anyway. Whatever. Go, leave. I never want to see you anyway.
Okay.
And so if you can smell it before the other one, that's telling you that the one you smell has the lower intermolecular forces, because they're able to get out and fly away, where the other ones are trapped with their buddies.
Got it.
But since we're here, oil and gas, you tell me who's stronger and why.
Okay. Oil.
Why?
Viscosity.
Yeah, right, because we know the gasoline just flows stupid easy and oil doesn't. Anything else?
Boiling point.
Do you know where gas and oil boil?
No.
Okay, so don't use that one.
Okay. Surface tension.
Yeah, I guess you could say that. And I would also say you can smell the gas.
Right.
Right. Okay. How about vinegar versus oil? And I'm going to go with Maria because I saw her mic's open.
Oil is stronger than vinegar.
Why?
Vapor pressure. You can smell vinegar.
Why else?
I think oil is thicker than vinegar. So viscosity.
Mm-hmm. I like it. How about, ooh. Pancake batter versus, well, I'll keep with oil just because I'll keep these in things that we should be able to know. Pancake batter versus oil, Ellen.
Pancake batter.
Why?
Viscosity.
Yeah, right. You try to stir that pancake batter, it's a whole lot harder than stirring that oil. And sometimes you only have one of these things to think about when you're doing these. Now again, I never once said what the intermolecular forces were on these. Now the first two definitely had polar and hydrogen bonds going there. The other two here were all just induced dipoles. Here, interestingly enough, I had something that was polar with hydrogen bonds versus a nonpolar. And this goes back to the fact that this molecule is way bigger. And so overall, its intermolecular forces are stronger overall. Now down here, we're not even going to talk about it because I have no idea what's holding pancake batter together. There's so many ingredients. All I know is it's thicker. That's all I need to know. And now I know that it has stronger intermolecular forces. So when you're doing these, when you're thinking about any pairings of molecules, just keep in mind these four physical properties that we just talked about, and they will give you all the clues you need to know who's got the stronger intermolecular forces. All right, 1.5 things to talk about. How we doing? We okay?
Good.
Okay. Ooh, I can do a shape on this one. Let's get all professional here. I want to talk about the heating curve. Wait, that's not what I wanted. Can I flip it? I did that wrong. Let me try one more time, and if I don't like it, I'll do it this way. Oh, there we go. And then I can take some other shape. I'm going to draw a general heating curve. So let me draw it, and then you guys can do it. But I'm going to try to make this all nice. Ooh, pretty good at this now. Oh, I say it right before I can actually, right before I missed it. Pride comes before fault and a haughty spirit before destruction. All right, what do I have here? I have the temperature in degrees Celsius on the left, and I have the amount of heat that we are inputting going along the bottom. Now, as we look, this is a generic curve. The slopes and the lengths of all these things are relative to whatever you happen to be looking at, but the general shape of this curve will be something of a ramp up, a flattening out, a ramp up, a flattening out, and another ramp up. Now, as we look at this, I want to point out that this area right here is where your solids reside. If you have a solid material and you start putting heat into it, the temperature will go up. That's a no-brainer. Now, at a certain point, you will reach a very specific temperature. This temperature right here. This is the melting point. Now, if we are continuing to put heat in, if we're continuing to pump heat into that, what happens to that solid when we reach the melting point?
Turns to a liquid.
What do we call that?
Melting.
Yeah. Okay. So now that we have gotten it and we've melted it, all of a sudden the temperature starts going up. And that's because we have now turned everything into a liquid. And if you have any liquid, you can continue to heat it up. You put energy into it, you will heat it up. You'll heat it up until you get to a really cool place. This really cool place right here. Oh no, undo. This place right here. What do you think this little spot right up here is?
Boiling?
Yeah.
Vaporization. Oh, I don't know.
Yeah, no, you're right, Frank, because that's what we're gonna do next. Because once we get to the boiling point, what are we doing to all that liquid? We are, say it, Frank.
Vaporization.
Yep. And once we turn it all into a vapor, of course, we are now a gas. And if we put more heat into it, we can heat up the gas. Now, we can look at this the other direction. We could actually talk about coming backward down this curve. If we come backward, we come down the gas, we cool the gas, we cool the gas, we cool the gas. And then what do we do to that gas? What if we're going backward?
Cool it.
And at a certain point, what are you going to do to it?
It's gonna become a liquid.
And what do we call that?
Condensing?
Yeah. Hey, does this look familiar, guys? Does this look familiar? We just took a test on it.
Yes.
Yeah, thank you, Miguel. So here we have the phase transitions. We see the phase transitions here. They're coming back. Now, go ahead. Was that you, Brenna? That might have been an accident. All right.
Oh, sorry.
It's all right. Never apologize in this class. I do not like, I'm going to put that in the syllabus, man. And big bold at the top. Anyone caught saying I'm sorry, I'm going to take points away. Never be sorry in this class.
Oh, wow. I wouldn't have done very well in this class then.
No, but I broke you of that, didn't I?
Yeah.
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 You don't apologize in this class. There's no question you need to apologize for. There's nothing. We're all strong people here. Or if not, I'll make you one. All right, I've done this heating curve. I've done this heating curve for a couple of reasons. It's important to realize what is happening when we look at taking any substance, starting from a solid. What is happening to it as it decides to gain and gain and gain or absorb heat? We talked about phase changes. We talked about the intuitive things. Well, of course, if you're getting it hot, it's going to get hotter. Yes, duh. But there is one very powerful thing on this curve that I think is probably escaping all of you. And you're like, can you just skip to the end? I'm going to pick on you, Miguel. You're my person for this one. You ready?
Okay.
Okay. If I'm heating up a solid, let's just say we have solid water, ice, okay? And I get to the melting point. What do you notice about the temperature for a while?
It's constant.
Yeah. And then I go ahead and I turn it all to liquid and I keep putting heat into it. And I get all the way up to the boiling point. Then what happens to that temperature?
It's constant again.
It's constant. And in fact, until you get rid of all of the ice in your icy water, it will stay at 0 degrees. That's the reason why I went over it for your experiment and I stuck that thermometer in the ice water solution and it stayed 0 while I went ahead and did the rest of the lab setups. And then I came back, oh yeah, I got to take a picture. It's going to stay 0 because all of the time that you're pumping in heat, all of that heat is going into just melting it. And it stays that temperature. And we're very thankful that on hot summer days when we go get that icy cold Coke, we put a lot of ice in there to keep it cold. Otherwise, it's going to heat up real fast. We heat up that liquid and we get to a certain point. We get to the boiling point. Now, as I recall, Ellen, you cook. It was either you or Laura or both.
I can.
You can? Okay, can you cook pasta?
Maybe.
Does anyone cook pasta?
Oh, you say pasta? Yeah.
Pasta. Yeah. How long does it take to cook pasta?
Maybe around 8 to 10 minutes.
There you go, 8 to 10 minutes. So whether you like it al dente or not, right? We all know, or at least a few of us know, that pasta takes 10 minutes to cook. Why do we know that it takes 10 minutes to cook?
It's about how long it takes for water to boil.
Well, no, we put it in only when the water is boiling. We know that it takes, hold on, there was a baker in this class. Who's the baker? Who's the one that bakes?
It was my boyfriend. He owns a bakery.
Oh, that's right. All right, so here, Sonia, right? How long do you bake a cake?
It depends on the recipe. Some of them take longer. Like 30,
every recipe says put it in the oven at 450 for this amount of time. Why do they put it in for that amount of time? Because they know the temperature. When I make biscuits and gravy, there's two ways of cooking those little Pillsbury muffins. It says you either put it in the oven at 375 for 15 minutes or 325 for 21 minutes. If you know the temperature, you know how long. Boiling water boils at 100. You put it in for 10 minutes. You're done. That's why it's so powerful. All of that heat you're putting in, all that fire isn't doing anything to that temperature. It's just making sure that the water keeps vaporizing. Well, what's the difference between like, you know, boiling and like stupid boiling? Nothing. You're just going to get rid of your water faster. They are both at 100. Now, of course, if you're at Denver, Colorado, do you cook your pasta for 10 minutes? No, because water doesn't boil at 100 in Denver. It boils at a lower temperature, which means you have to cook it longer. You can't speed it up. That's very powerful here, guys, that in this melting, all that energy is just going into melting. It doesn't heat up anything else. Polar ice caps, guys, trying to keep the temperature of this Earth constant. Anytime the sun hits the ocean and tries to vaporize that water, all that energy is going into that, thankfully not boiling off our stuff immediately. Imagine if you boiled your water and it all just went away. That'd be weird. Thankfully, it takes a lot of energy to do these phase transitions, and while it's doing it, the temperature remains constant. That is pretty cool. Now, so I'm going to give you guys an option. Do you want something for free that'll take about 15 minutes or so to do? Or do you just want to call it? The thing for free is not going to be on the exam. So I can either do it or I can just call the lecture here and then I can just tell whoever really wants to afterward. All right, I'm going to call it here then. Now, go ahead, Frank.
Can I hang around? It's like I'm not trying to like push it on anyone, but
no, that's fine. Yeah, we'll hang around after. What I'm going to do now though is continue. We are recording this, right? I did hit record.
Yeah.
Okay, good. Oh man. I told Graham that I would continue to record any questions about stuff that we've been doing with IMFs or polarities and things like that, so that when she watches it later, she can see it. So I'm going to keep this Q&A actually open on purpose because someone requested it. So now to the questions. Do we have any burning questions going on here?
Can you maybe give an example of what a test question would look like when you're asking about polarizing or polar bonds?
An example of how I might ask about polar bonds. Yeah, I would say something like, you know, draw ammonia. Is it polar or not? If you have water and alcohol, what's holding them together? And you would say, well, they're both polar, they're both dipoles or something like that.
Okay, thanks.
Oh, wow. This is going to be a short Q&A. I know what's really happening. You guys are just like waiting for the hour and a half to dissolve magically so you guys can go hang out with Melinda. I know how it goes.
I had to step away just when we're talking about the like comparing.
The what?
Comparing.
Okay.
Yeah. I just need to take a quick little snapshot of that. Just okay. Thank you.
Oh man, easy questions. Any other burnings? Oh, well, I guess I can stop recording.
Well, if nobody else is gonna say anything, I guess at the risk of going back, like,
What's wrong with going back? This is the whole point.
okay, how to figure out if I guess the parts of a compound are polar or non-polar.
So
I'm sorry. No.
So let me just do this. How about this? So even though this is a much bigger molecule than you would ever be asked on the exam, it's only going to be one central atom, and that's it. I'm going to go ahead and put up vinegar here. So this is, again, far beyond what we would do in this class. So take a look at this, Frank. Over here, I've got all these C's and H's. Is this part polar or non-polar?
Oh no, I misspoke. Not polar. What came after polar? The forces.
Oh. Oh, bummer. I was gonna love this demo, but okay,
well,
let's get rid of it.
Wait,
No, I'm throwing it away. I don't want it anymore.
put it back.
Why should I take it back now?
If anyone else needs the review, like I'm not gonna turn it down.
There we go. All right. So Maria, you wanted this. This guy right here, all these C's and H's. Is this polar or non-polar?
Non-polar?
Polar.
Polar.
Oh, wait. Wait. Where is it? All right. All those C's and H's, polars or non-polars?
No.
Non-polar. Right, we got all these C's and H's there. That entire aspect right there is non-polar. Okay. What about this CO? Is this polar or non-polar?
Polar.
Oh.
Okay. Again, what about that CO?
Polar.
And then what about this OH?
Polar.
Yeah. So even though we have a non-polar aspect of this, we have at least 3 spots here that are polar. And it's such a small molecule that we can clearly see the polar part. And that's why vinegar, this is vinegar, is a polar molecule. How else do we know that water or vinegar is polar? Even if we didn't know what it looked like, even if we couldn't do anything about it. How do we know that water or vinegar is polar?
It mixes.
Dissolves in water.
There it is, right? We know vinegar and water mix. They're going to do it.
So if we're given something like that in the future, would you call attention to, hey, like this is a makeup, but this is vinegar? It's like,
I don't understand that question.
Okay, so like in the book, sometimes it says, and I'm just gonna like pull out an easy one, like if you have water, like comma or in parentheses, like H2O, yada yada yada. It's like,
yeah, if you need that actual structure, then it would be given.
Okay, but we don't.
I'm not gonna give, at this point, I'm not going to give you guys water. That's crazy talk. But
right.
If I were to say give you vinegar, and if you needed the structure, then I would say, and this is its structure. But if I'm just going to say, hey, water and vinegar, which one's got the stronger IMFs? I'm not going to give you the structure. You don't need that. You can fall right back to these guys, the physical properties. So if you need the structure, it will be given. If it's not given, and you think it is, hop on. I'll be online. You can ask the question. But usually if it's not given, that should be your telltale sign that It's not needed. You're thinking in the wrong way.
Okay. We have a non-polar aspect over here on the left, and then we have a bunch of polar aspects on the right. And we decided that it was polar.
Oh yeah, absolutely.
Can you explain that a little more?
So there's a guideline, and this is for free because so the guideline is this. Four to 1 carbons to oxygens. Polar. 5 to 1, not. So basically, as long as you got like 1 oxygen or nitrogen in relation to every 4 carbons, you're going to be polar somehow, some way. You're going to be polar because that oxygen is either going to be stuck out all by itself, or it's going to have a hydrogen on it to fulfill octets, and those are going to have enough polar bonds relative to the nonpolar to still make it dissolve in water. For instance, some of you may recognize this guy. What's that compound? Nobody?
Hydrochloric acid? And I'm just like pulling that out of just because I see hydrogen and carbon.
It's sugar.
Oh.
Now, is sugar polar or non-polar?
Polar.
How do you know?
It dissolves in water.
It dissolves in water. And then, of course, we see a 1-to-1 ratio of carbons to oxygens in this compound. So that's a back of the envelope way, Frank, of knowing whether or not it's polar. And if you take a look up at our vinegar, we have 2 oxygens to 2 carbons. Yeah, you're going to be polar. The trick is, do you have enough things that are polar to override the nonpolar aspect? And that takes some experience. And if you have this experience right here, then you're good. If you don't, just ask yourself, does it dissolve in water or not? That's really, for this class, the bellwether.
Okay. But we're never going to be asked about something that we don't normally, like, that we intuitively wouldn't know if it dissolves in water, like some crazy, like, experimental substance that like nobody knows about.
Does anyone want to field that answer?
No.
There you go.
Okay, good.
I'm not here to trick you guys. I'm not here to try to make this any harder than it is. I'm trying to make it easier than it is.
Professor, if on the lab our drawings suck, are you going to take off points?
Only yours.
Okay.
No, I'm not.
Thank you for asking that question.
Everyone, I get some people in this class, and they just get in there and they're like, all right, so I'm going to take and I'm going to draw this.
Yeah,
No, here's what they do. They're like, there we go. I've got my oxygen. Ooh. And I'm going to put a little O in there, and it's going to be perfect. And then they're going to get another shape, and they're going to be like, oh, I'm going to draw these perfect lines coming off. Oh, look at that. No, stop. I have those people. They're great. They're artists in the making, and they make some good stuff. But yeah, no. As long as it's kind of legible, I'll be kind of okay.
I also have a question about the lab.
I'm sorry. Someone was very soft in their voice. Who was that?
Is it hard to hear me?
Yes.
Oh,
yes.
Okay. I'll try to talk louder. So,
wow, you're there. Good.
Okay, good. So, you said it might be a good idea if we write down the electron pair geometry and the molecular shape just as we go for each of them. I was wondering, are some of them just?
Some of them you can't do. So yeah, I think I know where this is going here. Nope, not that one. How about this one? So if we go to the actual experiment here, clearly for stuff like HCl, H2O, very easy to draw. You could draw this thing, and then over here, oh, I wonder if I can write on this. Can I? No, wait, is there a pen? Is that a pen tool? No, that's a signature. Don't want that. Don't want that. Get me out of there. Get me out. I don't want to fill in sign. Whoa, I thought I saw something up there. Dang it. Well, shoot. I don't want to do something bad here. Get me out of there. Is there an escape button? Can I do escape?
Hit close on the right.
Oh, I couldn't see it because your participant list is on my way. Thank you. Thank you.
Maybe
Is
the
it-
one right next to the signature. That one, yeah.
I'm looking. Oh, no, that's highlighting. Wait. Oh, edit. Maybe I can do that. Nope. All right. Anyway, so let's just say in these, you would draw that. And then on the other side for water, you say like, okay, so I got my water molecule looking something like this. And over here, I would say H, O, H, and I put my dots. That's my structural. Okay. If I go to some of the more complex ones, oh, and then sorry, and that wasn't your entire question. Your entire question now said you would say, okay, E pair is tetrahedral and molecular shape is bent. But if I go to a bigger molecule, one that is not easily done, so let's go ahead and go to, well, even H2O2. Let's do H2O2. So that's H2O, and here we have H2O2. I would expect you to draw it, right? And then you can have your H to your O, put in your stuff. But you got nothing here because you can't really talk about it. There's no central atom. Now, you could look at this oxygen and say, what is the geometry and shape around it? And then this oxygen and the shape around it. But there is no overall shape to this molecule.
Right.
So you would leave that one blank.
Okay. Would that also be the case for labeling polar or not non-polar?
Oh, but now you could, oh yeah, sorry. And then you could say polar, but on this one, you could still also say polar, but you'd have nothing else.
Okay, so for every molecule, you could.
Yeah, just about. No E pair, no molecular shape. But you could say polar. So, if you just sort of go through this, polar, non-polar. This one, is it polar or non-polar?
Polar.
Why?
Because
there's
the difference.
There's a
It's like
difference.
when you look at it.
Greedy guys on one side, not on the other. What about the one below it? Polar or non-polar?
Non-polar.
Because?
Because there's no difference any way you look at it.
That's right. All right, Alex, polar or non-polar?
Polar. Non-polar. Wait. Yeah. Don't question.
Polar.
You don't like this. Okay. Yeah, polar. Because there's right?
Because why?
Because there's when you look at it and change it, there's always like a little difference.
Yes, and if you actually do the structural, and this goes back, I think, to you, Laura, when you do the structural, you'll see that it has the lone pair sticking up here. And that lone pair on the central atom is going to make it polar. Same thing will happen on this guy. This one, what do you think? Polar or non-polar overall?
Polar.
Polar. We got a big polar and a meh. O2, what do you think? Polar or non-polar?
Non-polar.
Why?
Because they're just two. Because they're just two atoms bonded together. You can't really. You won't be able to see.
Be careful. These are two atoms bonded together, and this is polar.
Because though the first one, HC1, whatever that one.
HCl.
L. I didn't see that. Okay. Anyways, it's like two different.
It's two different. And down here, they are
It's the same.
the same. They're twins, right? So, not going to happen. What about C2H4, polar or non-polar?
Non-polar.
Why?
They're the same on no matter how you look at it from either side.
And it's all CHs.
Yeah.
What about this one?
Polar.
Because we got a difference. What about this one?
Polar.
Polar for sure.
Polar for sure, right? So we got an OH here. We've got oxygen or nitrogen battling it out, and that's actually a polar bond too. You got differences all over the place. This guy, polar or non-polar?
Polar.
Polar.
Polar. We've got the CO bond polar, the OH bond polar. CO2, polar or non-polar?
Non-polar.
Why?
Because there's no difference on either side. It's
okay. What
just-
about C3H6?
Non-polar.
Whoa. Hi, Alex.
Non-polar.
Polar. Yeah.
I want Alex to jump in there and say non-polar.
Okay. Non-polar.
Okay. Now why?
Oh, because yeah, I don't know.
Because it's just C's and H's.
There you go. It's all C's and H's. Even though it's clearly not like, quote, symmetrical or balanced, it's all C's and H's. All C's and H's. All right, what do you think about this guy? Polar or non-polar?
Polar.
Not Frank.
Polar?
No questioning. You say an answer.
Polar.
Polar.
Why?
There's a difference.
Not just a difference, but the NH is clearly a polar bond, and there's a difference, right? So we have to see that difference, and that difference has to have one of those guys that is a polar aspect. All right, this is vinegar. We already know this one. Duh. This is what is that? Ethaldehyde. Polar or non-polar?
Polar.
Polar, because we have one big polar bond and only one not. That's that whole 4-to-1 ratio I was talking about. Nitrogen, forget about it, right? It's a twin. What do you think about HCN? Polar or non-polar?
Polar?
Polar. We got the CN bond, very polar. We don't have it pulling on the other side. C2H2, polar or non?
Non.
Non.
Non. HOCN.
Polar.
Absolutely. We got a big polar bond here and a polar bond there. Done. What about this guy? Polar or non?
Non.
Because?
It's all C's and H's.
All C's and H's. So that's where you can just sort of look at a molecule and say, okay, we got a lot of polar aspects, and are they bouncing each other out or not? That was actually kind of fun.
So do we write the polar and the, where do we write that on the lab?
Wherever you want. I mean,
Okay.
in all honesty, I was just telling you to do that because it's going to help you. So whether or not you write that, or whether or not you write the electron pair geometries and the molecular shapes, because clearly that lab manual doesn't have a spot for it.
Well, I was thinking the electron dot box because we don't write anything there.
Yeah, if you happen to have one of those lab manuals that has that column still, absolutely. Go ahead and write it there if you want.
Okay. And then for the model, we just draw like a picture of what is online?
Yeah.
Okay. Does that have to be in color?
No.
Okay.
And as we already established, it doesn't have to be pretty either.
Well, I'll
I think-
probably color it though.
I think you just answered it, but did you say the structural formula just has to be the symbols and then the electron dot, then you add the dots?
Wait, say it again. You broke up a little bit.
In the lab, there's a column for structural formula and then electron dot.
We are not doing electron dot. Yeah, we will not do electron dot because let's go back to this guy. Let's go back to this guy. So if I were to draw this
Yeah,
out.
I started drawing some electron dots and it got ugly.
Yeah, it's ugly fast, right? 'Cause you're going like this, and it's just freaking tedious. And you're going like this. And you know, what does this end up serving us, right? So we can see all the dots. Big deal. This is right.
Okay. Can I show you what I did? And
Go for it. I'll stop sharing. You share. Still recording.
So I put electron dot. I mean, what you did, I put in the final answer in the electron dot. But in the first one, I just put before you put the dots and the final lines, the bonds.
No, I'll take that. I'll take that. But I would encourage you when you do your structural there to do the one you did in the final column. And the reason you want to do that is because that will now let you know when you need to bend it or not. Okay, so if we go back to the beginning of this lecture, when we were doing these, and then Julio asked this question: why is this linear but this one not? The reason why you keep all these lone pairs when you do your structural is to know that, oh, that's taking up space. I now need to bend it.
Okay.
Because if you just did something where you said like, oh, I'll do SE, then an S, and then an SE, and I don't do any of my lone pairs, how did I know that was going to bend? So I would encourage you to, what you put in the final column, to be what you do when you do your structurals. But what you've done, don't erase anything. You're doing it just fine. Just keep what you've done. Just realize you want to do that final column if you're going to draw them out on the exam to get a reference.
Okay. And on H2O2, you just drew that, but I did it straight across instead of bending it.
Oh yeah, that is horrible. That's the worst thing I think I've seen in the last 35 seconds. All right. The reason why you don't want to do it straight, okay, is clearly in the model right here, we bent it, and that's important. It's very important that you do that, just like we did the other day. It was very important that you draw water like this and not like this. This would imply that it was non-polar. And if you did H2O2 like that as well, you're thinking it's non-polar. Oh, it's very polar. And the fact of the matter is, these oxygens being so exposed like that is the reason why it does what it does, and that is namely eat all the bad tissue when you scrape your knee. I'm actually just gonna get rid of this.
Well, and isn't it because in the picture where you have your covalent bond or the lines and the dots, and they want 4 bonds or 3 bonds, so oxygen wants 2 bonds, and it shows you that one's bent. Is that the same reason why H2O2 would be bent?
Yeah, because those oxygens are on the inside of the molecule, so they will bend that molecule.
Okay, thank you.
Okay, so for the structural formulas, do you want us to put in the electrons?
Yes,
or do we just?
Absolutely.
Okay.
Absolutely.
That's kind of where we were a couple of nights ago. It's like we were looking at electron dot, and it's like, okay, so he wants electrons over here, but no dots over on structural.
No, every structural formula that I've drawn has all the dots all the time. And again, that's to remind you, how many lone pairs do you have sticking out? Why is it straight, versus bent? Because you need to know where those lone pairs are. If you came up here and you drew NCl3 and you didn't have any of these dots on it, how would you know to even put the NCl3 as a trigonal pyramid? How would you know?
Right.
So keep those lone pairs going. Keep them going.
Okay.
If you have carbon and sulfur in the same molecule, what do you put in the center? Carbon or sulfur?
How many bonds?
I'm sorry, CS2.
CS2, right?
Mm-hmm.
So who makes more bonds, carbon or sulfur?
Carbon.
Hold on, here we go. Who makes more bonds, carbon or sulfur?
Carbon.
Carbon. Who's written first, carbon or sulfur?
Got it. Thank you.
Yep. So all these little cute clues are going to help you. So that's why I always go through every single time, like, you know, why do we know? How do we know? It was written first, it's probably in the middle. If it makes the most bonds, it will be in the middle. So there's a reason why, actually, if we go back here to the end of this lecture here, you know, there's a reason why we said it's, we said that it's SO2. That is to imply that the sulfur is going to be in the middle. It's not written as OSO, while I could hardly bear to see it written like that. Come on, guys, that was good.
Oh, that is funny.
No one? Only Frank?
Sorry, I wasn't really paying attention.
All right, so Maria, I said we write SO2 to remind you that sulfur's in the middle. And while someone might write it like OSO, I couldn't bear to see it written that way.
That's a good one.
Thank you. You know, we write the S first to say put it in the middle.
Okay, I have a concept question.
I like it.
When you're ready.
I'm always ready.
Okay. So I haven't read chapter 11 yet. So I'm still kind of trying to grasp this concept.
I love when somebody comes in with a disclaimer of like, so I haven't really been paying attention, but I have a question.
I've tried. So whenever the lone pair, so I guess my question is, so whenever lone pairs appear, the rest of the, I guess, elements are just trying to get away from it? Is that where the bending happens?
Yes.
Okay. That's it for now.
In a normal semester, again, I have all this physical humor I could do. I would normally form a bond with a couple of people we'd reach out and hold hands, and I'd start shaking their arms for the movement of the electrons, and eventually they would like stop me from shaking their arms so violently, because why would you do that? When electrons are shared between the atoms, those two nuclei sort of keep those electrons from going cray. But then what I end up doing with the students is I'll let go of one of their hands and just start flailing my arm, and you'll watch the student like back away, like, what are you doing? Well, you're not controlling the electrons, so you're backing away. The same thing with the lone pairs. If there's no other atom trying to hold on to them, it kind of gets a little out there. As I often say, it's that one uncle at the family get-together. You just kind of leave that uncle alone.
I'm that uncle.
I for sure got one of those.
Could you perhaps walk me again through CS2, like actually doing the structural formula? I just don't know where to take away the lone pairs to make the, like which lone pair, where do you leave the lone pairs?
Okay, so can we agree that we're going to start here, Carla?
Sure, I bent it, I don't know why.
Yeah, never bend it. So, okay, let me be very, very clear, because you're not the only person who wants to do this. Whenever we go here and we look at these, as soon as I tell people, oh, bend oxygen, they bend everything. They want to bend everything. I'm like, no. Carbon doesn't bend. You're writing your notes with a pencil. That pencil lead is made out of carbon. Try to bend that carbon. What's going to happen to your pencil lead?
Yep.
Yeah. So don't bend it. Even if you do, okay, hold on. Let's go ahead and do this. I'm going to do it for you here. So this has 6 times 2 is 12 plus 4 is 16 electrons. Are you okay with that, Carla?
Yeah.
Okay. So I'm going to say that I've already used 2, 4, 6, 8, 10, 12, 14, 16, filling from the outside of the molecule inward. I'm going to go ahead and do it down here for you too. Nothing should be different there. Are you okay that you don't touch the carbon yet?
Yep.
Okay. So at this point, what I do is I notice that sulfurs are okay, but the carbon is not. And so how do you do it? How do you know? You just take any two, I don't care, and put them there. Take any two, I don't care, and just put them there. This is technically right. We can do the same thing down here. Take two, put them there. Take two, put them here. But in your bottom one, what is over here that says that the sulfur can't just move up there? What's pushing it?
Yeah.
Right? So when you see like, oh, that's weird, there's nothing there. Well then, you know what? Get up there like you should be. Get out there like you should be. Now, let me be clear. So if we do again, say something like maybe just, well, I hate picking on SO2, but SO2 is so good. If we have SO2 and we draw it, this has 18 electrons. I've used 2, 4, 6, 8, 10, 12, 14, 16, and now I have the 2 here to make 18. And I'm just going to draw one of the resonance structures. I will take, I don't care which, I'm just going to take a pair and share it. So now everybody has their 8, and their 8 valence electrons. But this is where I'm going to notice I have somebody taking up space. Someone's taking up space. And so I'm going to have to now bend this thing because that lone pair is taking up space.
Got it.
Now we have a reason to run away. Más preguntas.
You mentioned that we were going to talk about something after class that wouldn't be on the test, but it's just like something cool to know. Are we still going to do that, or are we going to do it now, or are we going to wait till like?
I'm going to wait till people are done with questions and they want to just learn the cool thing.
Okay.
Is it surfactants?
Yep.
Oh my god.
Wait, did I get to this with you guys, Melinda?
Oh, yeah, last summer.
Yeah, okay.
Sorry, my dog's barking.
That's fine.
I thought she was excited about the, what, surfactants? Or?
Surfactants, yeah, she is, because she realized just how cool this thing is.
It's super cool.
For lab 6, for the...
Is that the flame test?
Yeah, the flame test lab.
Thank you.
For the unknown solution, we're just supposed to do one of them, right? There's 3.
No, do all 3.
Okay.
Do all 3 and just, you know, make yourself extra lines for it.
Okay.
I guess I should send an announcement to that.
Yeah. Oh, I have another question. For the longer molecules, how do you know which molecule or which, gosh, I don't know what they're called anymore. I guess which element sticks to which element?
Well, first we just built it to show you.
Okay.
So, but I will say this. There are ways of writing these compounds, and then there are ways of writing these compounds. Let me be clear. Let me go down to, let me get down to this guy right here.
Mm-hmm.
That's vinegar.
Okay.
I know it's vinegar, and so this is just because. I know it's vinegar because I wrote it as CH3COOH. Okay, and this is for free. This is for free. But if I didn't do that, so if I wrote, what's that going to be? C2H4O2. If I didn't tell you, I could have CH3COOH. I could have, let's see, this guy. I could have this guy. I could have this guy. All of those have exactly the same number of carbons, number of hydrogens, and number of oxygens. Here we have vinegar. Oops, hold on. We have vinegar. We have 1,1-ethylene diol. We have cis-ethylene diol and trans-ethylene diol. All of them are correct drawings. However, if I wanted you to draw this one, I would have said make CH3COOH. The others would have been a free-for-all. So in the lab, I have tried to with these molecules, especially because normally you would build them from scratch. With this, I would say you look at the molecule and say, oh, I'm going to do a CH2, done. Attach it to a CH, done. Attach that to an NH2. So in some of the smaller organic molecules like this, if they want a certain structure, they will write it a certain way to help guide you. Otherwise, all bets are off. And as long as you're fulfilling octets, you're fine. So I don't know if that was what you wanted.
Yeah, that makes sense.
Okay.
So I can kind of just break it up and attach it.
Yeah, absolutely.
Okay.
All right. Any other cool questions?
Just to clarify, just to make sure, I'm pretty sure I understand it, but yeah, anyways. With the double line, that means like that equals to when you have the two little dots around them, that equals 4.
So a line means 2 electrons.
Mm-hmm.
So if you have 2 lines, that means 4 electrons.
Oh, right. Okay.
So did that answer your question?
Yeah, and then one line would be 2.
Right. And 3 lines would be 6.
All right. So, all right. Yeah. Okay. Thank you.
Mm-hmm. There's something in a chat? Whoa.
I was trying to be.
Oh. Do you want to take that one, Melinda? Uh-oh, is she still here? Oh, she's gone. No.
Uh-oh.
Now I feel sad and afraid.
And you like scroll down, you'll see her picture, and that's the link you click on. She only posted it once.
Sorry, I missed the first half. What did you say?
If you go on the announcements and like you scroll down, you'll see her picture, and that'll be the link you can click on, and it'll always be that one link.
Thank you.
Uh-huh.
I have another question about Lab 6.
Okay.
For our observations for the colors in the flame test,
yeah,
how detailed do you expect this to be?
So in a normal lab, I would tell you to be as detailed as you can in the blink of an eye.
Okay.
Colors and smells are visceral responses to people. Okay. When they smell something, it immediately triggers a memory or a thought. Same thing with colors. It'll automatically do that to you. So someone's burgundy red will be somebody's wine red, will be somebody's deep red, will be somebody's, you name it. But the idea is that when you look at that color, if you just go with your gut will always tell you the right color. Because That way you don't get caught up in some weird nuance thing. Like my favorite color is the blue right at sunset. And some people have called it a cobalt blue. All I know is it's the blue that makes me happy. And so if I ever see that blue, I know exactly what that blue is. So I don't want you to get caught up in being overly specific or overly generic and just go like red, got it. Orange, got it. It's not orange, it's pumpkin orange. It's bright orange, it's neon orange, it's, you know, whatever comes to you.
Okay.
Professor, I have a question. I just noticed, and you probably said this before, but I just noticed when you're looking at a molecule like CH2Cl2, the first letter, it looks like it's always in the center. Is that the case? Like the first letter of the molecule will always be in the middle?
Yeah, especially for these ones with just one in the middle. So there we go, CH2Cl2. Yeah. The only exception that I can think of right now is H2O.
Right.
But yeah, the first one is almost uniformly the one in the middle.
Thank you.
When you say almost, and it's like I caught the almost. I'm pretty hesitant to go by that rule because we were talking about like boron as another example. You know, almost all of them are looking for 8 electrons except for boron and hydrogen.
Right. For every rule, there's always exceptions, Frank.
So how many like ballpark exceptions will there be or are there to like?
Well, let's take a look at this lab, man. Take a look. Who's in the middle? Carbon. Who's in the middle? Nitrogen. Who's in the middle? Nitrogen. Who's in the middle? Carbon. Who's in the middle? Carbon. Oh, look, carbon. Now, where's the exception? This guy. Where's the exception? This guy, because we're trying to tell you how to build it. Where's the exception? This guy. Other than that, if you're first, you're in there.
Okay.
So I would worry less about memorizing or knowing the exceptions and just basically go with the general rule and you'll almost never be wrong. I can't think of a time that you would be wrong. Well, no. Okay, let me be very clear because I've seen this. All right, I have seen the people go like, you told me that the first thing that's written is going to be in the middle. So I'm going to put an H here and an H here and an O here. Would you ever do that, Frank?
No.
No, because you know better. You know that oxygen has to be in the middle. Hydrogen can't be in the middle. It can only form one bond. So the exceptions will be painfully obvious that it's wrong if you just blindly write it down and be like, oh, yeah, no, that can't happen. So don't worry about memorizing the exceptions. They will make themselves well known early on.
Okay. It's like accepted, but when I hear that, I worry about like the boron from the other day. That I'm like, yeah. that Miguel it was like, I worry about that because I wouldn't have known.
You need to not worry about that so much. My exams are not about the exceptions, guys. They never have been. Worry about the exceptions when you get to upper level chem courses and you got to figure it all out. This isn't that, man.
Okay.
This is getting your feet wet.
Are you going to throw in questions that that you haven't talked about or homework we didn't do? Or
why would I do that? Why would I do that?
I remember this.
That's crazy talk.
No, just a guess. Might have happened before.
No, I've never done that. I think that is the most disingenuous thing to do to somebody.
All right.
Here's something. I've never talked about, you didn't do any homework on it, but it was in the book, so I'm throwing it in there. That's crazy.
Okay.
All right. Here's what I'm gonna do. I'm gonna take a quick potty break. I'm gonna be back. I'm gonna do that special little topic for anyone who's sticking around. You can also formulate last minute questions that I can answer before I do it. So I'll be right back.
Are you gonna keep recording?
I don't know, should I?
I mean, isn't the file gonna take a long time to upload later?
Yeah. So you want me to stop the recording?
It's up to you.
I'll stop the recording. No. Boom.